Now, when we look around our solar system, there are these great patterns, wonderful patterns, particularly these patterns of motion. You know, everything orbits and rotates and spins counterclockwise, great patterns. But there are exceptions to these patterns. Exceptions to the patterns. There are some moons which orbit their planet different directions. Some moons orbit the wrong direction or at some angle. So moons which orbit different directions. Directions. That's interesting. Why? I mean, okay, we got the nebular theory of the formation of our solar system. It all started out as one big spinning cloud of gas and dust that then collapsed down and gravity makes it fragment into pieces. That's great for explaining the overall patterns. We need to explain it all. This is interesting too. Here's another interesting exception. The Earth has a big moon. Our moon is huge compared to other moons. Now, okay, there are other moons in our solar system that are bigger than our moon. Ganymede, Jupiter's moon, is, you know, larger than our moon. But as a fraction of Jupiter's mass, Ganymede's tiny, you know, it's like a tiny, tiny fraction of a percent, whereas our moon is like, what, it's somewhere in the neighborhood of 10% of the Earth's mass. That is way, way out of line of the mass of other moons in our solar system. You look at all the other moons in our solar system, yeah, okay, Ganymede's big, but it's still a bajillionth of a percent of Jupiter's total mass. Our moon is huge. And that doesn't fit the overall pattern. You know, okay, like, you know, there's the sun, you know, the solar system is 99.8% sun, and then 0.2% is everything else. Similar thing holds in like Jupiter's system. You know, the Jupiter system is like 99.8% Jupiter, and then there's, you know, 0.1% or less, which is its moons and things like, so that overall proportion kind of works. In Jupiter or Saturn or wherever you're going. Then you look at our our system, the Earth and our moon. Our moon is enormous, and, you know, let's face it, you know, Mercury and Venus don't have any moons at all. How come the Earth not only got a moon, but got such a huge one? That doesn't fit the overall pattern in our solar system. Other things, Venus does not spin counterclockwise. It orbits the sun counterclockwise, but it spins clockwise. Spins very slowly too. Spins clockwise. Slowly. Uranus spins on its side. Uranus orbits the sun counterclockwise like everything else, but it spins on its side. Spins on its side. So how do we explain these exceptions to the, you know, the overall general pattern of motion in the solar system? Well, first of all, we can look at the moons, and we start studying them, and we see that these moons which orbit in different directions tend to, looks like there was some sort of violent event in their past. And so our hypothesis, and then we study it and we test it and it becomes good, it becomes a theory, is that these moons were captured. Now, being captured by gravity is not an easy thing to do. You can't be just the moon floating around and you go close to the planet, oh, I'm going to be, you know, just an object of asteroid, something floating around. I'm going to be a moon around here. Because every captured object has less energy than every free object. So, I mean, as this asteroid comes floating by the planet, it goes faster and faster and faster. It has more kinetic energy, which causes it to just keep going. So, in order to get captured, that's a hard thing. You have to lose energy in some way. Conservation of energy. You know, energy can't be created or destroyed. If you have some energy and you're free and you got to get captured and turned into a captured moon, you got to lose energy in some way. So that's a tough thing. Basically, it means you have to lose it through, say, friction if you pass through the planet's atmosphere, or a collision with something else that can send energy into other places. So that's why the vast majority of moons in our solar system were not captured. But there are a few of these exceptions, and then we start looking at these captured moons, and it's like, ooh, this moon smashed into something long ago. So that's an interesting thing. So that kind of accounts for this exception. But the Earth has a big moon. Venus spins counterclockwise slowly. Uranus spins on its side. What explains that? Well, again, let's go back to the nebular theory of the formation of the solar system. You got a great big spinning cloud of gas and dust. The gas, most of the stuff falls into the center to become the sun. To make planets, you need solid objects, the little pieces of dust which stick together, making dust bunnies, bigger and bigger things, and things the sizes of houses, things the sizes of mountains, things the sizes of continents. And when you have gravity pulling together things the sizes of continents, well, now that's an event. That's something here. When these things are smashing into each other, that's a colossal sort of thing. So initially, the process of planet formation is slow, careful, steady, well organized, and then as you get bigger and bigger, things blamming into each other, merging two different things, hitting together, merging together to become one bigger sort of thing. That's a violent thing. And when you have big violent things going on there, these things can be explained as a result of the last steps of formation. Last steps of formation. And we call this the planetesimal era. Planetesimal era. You know, it's not the planet era, it's the planetesimal. You know, it's a tiny little bits of planet sort of era. And during this planetesimal era, this is when you have, you know, big things going around smashing into each other. And so, right, this makes sense that, okay, some big thing is going to, you know, hit Uranus and knocked it on its side, and something's going to hit Venus and knocked it so it actually spins backward very, very slowly. And we think our moon is accounted for this as well. When we run simulations about our moon, it's very hard to get our moon to form together with us at the same time. But on the other hand, it makes total sense. If the computer simulation is just wonderful. You know, the way to form the moon is you take this young Earth, which is just forming, and then you take some object about the size of Mars, and you smash it into the Earth, and then debris from, you know, the Earth's mantle and all this sort of stuff then ends up in orbit around this, and some of this gets pulled together by gravity. And that's a way you can form a moon, which is, you know, 10% of the Earth's mass. Not by a slow, steady process like everything else, but now big collisions. So that's cool. So this tells us something. So these exceptions to the pattern tend to be accounted for very well by the existence of a planetesimal era, the last little bits of formation where big things are smashing into each other. And then this would stir things up a little bit. And so you get a few of these exceptions here. Another key question, another thing we got to be thinking about is, how old is the solar system? How old is the solar system? I mean, this is a good question. You know, okay, so we're buying this picture. You know, this theory of the nebular theory of formation. You know, big spinning cloud of gas and dust. That works. That makes sense. It totally explains things really well. But when did it happen? I mean, was it a million years ago, a billion years ago, a trillion years ago? How do we get specific numbers on this? So to define this, we can date rocks on the Earth from the moon, and even better, from meteors. Meteorites. Rocks that have fallen to the Earth from space, come screaming down from space and hit to the Earth. Now these things are probably some of the oldest stuff on the Earth. The Earth is dynamic. You know, new rocks are being made where volcanoes erupt and all sorts of crazy things are going on. But now a meteorite out in space, you know, that's a leftover from the from the solar nebula. It gets pulled together, you form your little chunks and stuff like that. And this never quite got incorporated into a planet until today. And then it falls to the Earth, and now it's part of the Earth, but now we can measure it. So how do we measure the age of a rock? How do you figure out how old it is? People, you may have heard of carbon dating. It's like that, but it's not carbon dating. Carbon dating only works on material which used to be alive. So there are there's different forms of carbon. So, you know, carbon is an atom. It has, you know, 6 protons and 6 electrons and then different amounts of neutrons. And if you've got, let's see, what is it, 6 protons, and if you've got 8 neutrons, then you get what we call carbon-14, which is radioactive. That's created in our atmosphere by cosmic rays from space coming in, and then it gets absorbed by plants. And then plants, you know, incorporate, and then the animals eat the plants, and then the animals or the plants die, and then the carbon-14 gradually decays away. And so any living thing today has a certain proportion of carbon-14, and then older things from the past, you know, has less and less and less carbon-14. And so that's how we date living things. But that one, I want to date a rock. The rock wasn't alive. And I also, carbon-14 doesn't go back that far. It can go back many, many, many thousands of years. But I want to talk about things that are hundreds of millions to billions of years. And by that age, all your carbon-14 is gone, even if you had it to begin with, which if you were a rock, you didn't. So, but we use other radioactive isotopes. For instance, we use potassium, potassium-40. There is an element which decays into argon, argon-40, over a very long period of time. So here's the idea. When you're making a rock and the solar system and all this sort of thing is forming together and all this, well, your argon, what's argon? Argon is a gas. This is a gas. This is not going to stick together. This is not going to get incorporated into rocks. You know, it's not going to, it isn't going to do your dust bunny sort of thing like this. Potassium, on the other hand, argon is a noble gas. It doesn't even combine with any other elements. Potassium combines with things. It can work together. It can be solid. It can be incorporated into things. So if I build a rock, you know, in the very beginning of the solar system, it can have, radioactive potassium-40 in it. It's not going to have any argon-40. It's a gas that would float away. So what happens is today, I take a rock, and I take it into the chemistry laboratory, and I measure, it's got some potassium-40 in it, and oh look, it has some argon-40. Where'd the argon-40 come from? It used to be potassium-40. The only way you're going to get that into a rock is if, it starts out as potassium-40, and then it turns into argon-40, and now it's trapped in the rock. It's not going to get away. There's no way for it to escape once it's sealed inside the rock. And then you measure the proportions, and we know how quickly it's a very, very long time scale. It's where, potassium-40 turns into argon-40. Carbon, that's thousands of years. This gets us into this allows us to measure ages of hundreds of millions and billions of years, because this is such a slow process. If I find that, there's equal amounts of potassium and argon-40, well, it tells me half of the potassium is turned into argon. If, on the other hand, I find very little potassium-40 and a lot more argon-40, it tells me, most of the potassium is turned into argon-40, this must be older. So the older the rock is, the more argon-40 and the less potassium-40 it has. A very young rock has potassium-40 and no argon-40, and so we can use this to measure the dates. And this is how it works, and we can do the mathematics and we can work it out. And we find that the oldest Earth rocks, go back about 4 billion years. And then we go to moon rocks, and of course the moon doesn't have active volcanoes anymore, it doesn't have erosion, it doesn't have all these things which are, constantly stirring things up in the Earth. And we find that this gets older, and you can get to around 4.2 billion years, and then you get your meteorites. These rocks which fell down from space, landed on the Earth, we pick them up, we study them, and we find that these go to about 4.5 billion years. The oldest meteorites we find have an age of about 4.5 billion years. And then we find rocks from other sources and all this sort of thing, and we start looking around and they kind of converge on this. And so that must be the time. That's our evidence. We know the oldest Earth rocks are about 4 billion years, and of course the Earth is constantly, the crust and the earthquakes and all this sort of thing and erosion away. So, the Earth is a dynamic place, so that's younger. But the meteorites, they've just been floating through space ever since they formed. And they give us an age of 4.5 billion years. That's how we know. Our solar system formed roughly about 4.5 billion years ago.